Let's have a little reminder of functions. So the first lecture we only dealt with linear equations, and of course we know there's different types of equations. How we knew we had something linear is we would plot point by point and they would be in a straight line, and then we'd connect the dots. Well, what if I wanted to plot this equation and I just picked various values of x? For example, I could say let x equal 0, then y would equal 9, and I could plot that, and I could do this for various points. Well, away I go. In this column, I'm going to pick values for x. I picked -4 through +4. As you can see, to find the y value, I simply plug the x values in, and that gives me my y value, which gives me an actual xy data point. So these points now I can plot on a graph. So here I've plotted the points and I can connect the dots. And as you can see, this certainly is not linear. And some of you may have remembered x squared, a parabola, when it has a negative out in front of it, is why it's upside down. If you didn't, that's why we're reviewing, right? So in this last example, there was a correspondence between the value of y and the value of x. I like to call the y the dependent variable because my y depends on what my x is. And so that's kind of a nice way to think of the y variable, because when you graph data, and a lot of times you don't know, well, what goes on the x-axis, what goes on the y-axis, see which one really depends on the other when you're analyzing your data. This correspondent between these paired data is what's called a function. I've always liked this example that you have this little function machine, you input something into it, the function does something, such as it might square the number and then subtract 3, and then it outputs a value. So notice we're changing from our y to now this f of x because we're calling y a function of an x, where our x is our domain and our y is our range. Other correspondence, of course, an item could correspond to a price. Student corresponds to a grade, employee corresponds to salary. If you notice what all of these have in common, a student can only have one grade, and that's important to have a function. So in other words, when you have a particular, and here even an employee can't have different salaries, they can only have one salary, and that's that one-to-one correspondence. So one input only corresponds to one output. So our function definition says we have a correspondence between two sets such that to each element in the first set there corresponds one and only one element in the second set. In other words, each domain has only one range. This would be a function because one x goes to one y. Doesn't matter that this same x, in other words, this could be two students, certainly can both make A's, right? But over here, I couldn't have this student made an A and then also made a B in the same class, of course. That would not be a function. Functions are specified by equations. So for example, if I asked you, is this a function? Well, if you solve for y and see if you put in a value for x, do you only get one y? So I solved this for y, I added 3x to both sides, then I divided every term by 4, and I can see for any x that I plug in, I'm only going to get one y value. Is y squared equals x a function? If you remember, when you solve something squared, you square root it. Now this kind of gets forgotten over here, is when you square root both sides, the other side, you do the positive and the negative. So as you can see, this is not a function because if I put in an x, I could get in a positive y or a negative y. Vertical line test is kind of nice because that's a very fast way to tell if something's a function. We simply draw a vertical line, and if I hit the graph in 2 places or more, then it's not a function. So if you hit it more than 1 time, this vertical line test then says that would not be a function. This would be a function because anywhere that I draw a vertical line, I'm only crossing the graph once. So again, we're going to talk about this function notation where we start out with equations, and typically that's when you want to solve for particular variables. And then we say, well, instead of y, let's call this f of x because I'm inputting an x, so my function is in terms of x, f of x, and when I input my x, I also plug it in here, and then that gives me the value of my function. So if I wanted to evaluate a function for a particular value, I just simply plug it in. So I replace the x with the value of -3, and then I evaluate the expression. There's my -3's. And I see here, you remember that, oh, please excuse my dear Aunt Sally? I do this first, my exponent, so -3 times -3 is a +9, and then 9 minus 9 gives me 0. Which means the point -3, 0 is on the graph of this function. What is the domain of our last example? Now, I've always remembered domains, or domains are good x's. What could I plug in for x so that there's no problem? I think I can plug in any value for x, right? I don't see any reason that I can't pick any value. Nothing's going to happen if I plug in a negative value, if I plug in a fraction, if I plug in 0. It looks like I can plug any value of x. And that's when we say the domain is all real numbers, or from -infinity to +infinity. What about the domain for this one? Well, you have to be careful with square root, because if what's under the square root is negative, you can't take the square root of a negative number, unless of course you're living in that imaginary world, right? So if I plugged in 0, I end up with a negative under my square root. So apparently 0 won't work. Well, how can I tell what my domain is? Well, if I say where is this function defined, it's defined only for values under the square root that would be positive. And how we write that in math, positive numbers would be greater than or equal to 0. So if I solve this, add 2 to both sides, and then divide by 3, this says that my domain is from 2/3 and anything beyond it. And it includes 2/3. That's why we have the square bracket. So if I plug in 2/3 here, what's going to happen, I'm going to have 3 times 2/3 minus 2. The 3's are going to cancel. I'm going to get 0. Well, the square root of 0 is okay because that's 0. And then anything larger than 2/3 will always make this piece larger, so you'll always have a positive value. Find the domain here. What if you plugged in -3? Bad things happen, right? You can't divide by 0. So you have to worry about your domain when you're dealing with rational. Remember, rational is a polynomial over a polynomial. And so in that last case, sorry I hit the slide forward, is it could be any value except what makes the denominator 0. All right, this difference quotient. Using function notation, so f of x equals x squared minus 2x plus 7, find f of a. So this is the same thing. I'm evaluating this function. Everywhere I see an x, I simply plug in an a. Well, how about we evaluate it at f of a plus h? everywhere you see an X, even though it might feel a little weird, but everywhere you see an X, you plug in an A plus H. And then, of course, I can square this out. Remember that that means A plus H times A plus H. And I can, of course, distribute my -2. I could put together the last two examples, meaning I could find f of A plus H minus f of A. So I went ahead in my f of A plus H, I collected common terms, I canceled things, whatever to make it look better. And then, of course, I have my f of A. So if I subtract these two and I cancel things that are going to cancel, notice the A squared, and we're going to distribute that. So that's going to cancel. The 2A's cancel, the 7's cancel. I said, do you notice anything interesting? And this is very important. When you do the difference quotient, if you do it correctly, everything that's left should have an H in it. If it doesn't, then you need to back up these steps and just, figure maybe you didn't distribute a negative correctly. So that's very, very important. If, when you finish this difference quotient, the numerator, you're going to see that's a whole piece, every one of these should be in terms of H. So the actual definition of the difference quotient is all of those pieces together. It's taken f of A plus H minus f of A, and now hopefully you can see why you would have everything in terms of H, because we're going to end up dividing out those H's. So I have my numerator here, and then my denominator, I can cancel out some H's and end up getting this answer. And we'll talk about more what that answer means, but this is in your math packet, this difference quotient, and this is very, 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 very important. Very. All right, let's talk a little bit about mathematical modeling. When you have a model, you have data, and then you look at the data and you model it to equations. So that's how they come up with these datas with these equations with this historical data, and then they look at it and they say, oh, well, if my data kind of looks like this, it looks like it might be quadratic, and so I could fit it to a quadratic equation. So business mathematical modeling is one thing that's important is any manufacturing company, of course, has cost and revenue. If the company has a loss, then revenue is less than cost. Not a good thing, right? The company breaks even when revenue equals cost, and the company will have a profit, of course, if revenue is greater than cost. You have fixed cost and you have variable cost. Fixed cost is you got to pay it no matter what. You don't sell anything. Okay, you set up the machine to make all this product, but nobody bought it. Guess what? You still have to pay setup fees. Variable cost is the cost per item. So in other words, if it costs $1 to make something and you make 5 of them, then it costs $5, right? 5 times that dollar. If I let X be the number of units manufactured and sold, then we could come up with a cost function that would be our variable cost plus our fixed cost. As you can see, this is linear. This is my y equals mx plus b, just use different letters, where these are just simply our constants that we put with our fixed cost and our variable cost for whatever the context of the particular problem. So we have these price demand functions that are typically established by financial departments, again using historical data. They're used for profit loss analysis. So for a price demand function, we could let X be the number of items that can be sold at $P per item, where M and N are constants, again determined by the particular context of the problem. If revenue is the number of items sold times the price per item, where X is the number of items sold, then revenue would be the number of items, X, times the price. Well, we just said that P was this piece right here, so I could plug that in for my revenue. and then I could find profit by taking revenue minus cost. So these are some formulas that hopefully you kind of already, being business majors, you kind of already know about revenue, profit, cost, but I would put them on my formula sheet. How do you find revenue? X times P, where X is the number of units, P is the price. A lot of times this cost function will be given to you. It could be written out in words in the problem that you just have to figure it out, but a lot of times that's given to you. All right, a manufacturer of digital cameras wholesales the camera to retail outlets throughout the U.S. Below are the price demand data given. And if you notice, when price goes down, demand goes up. Makes sense. I'm going to buy more when things go on sale, right? An analyst so nicely gave you this price demand function. So this is in that form, maybe moved around, the mx plus b. And we have a domain here. I want to plot the data in the table and then graph the price demand function. So here's the plot. These are just data points, right? So when x is 2, y, or p in this case, my price is 87, and so on. If I graph this line now over these data points, why is it not exact? Remember, the data values, these are actual data values, and my line is a best fit line, so it's not going to be exact. My analyst did pretty good with this equation. He best fit it, but he's not going to get exact. If we could get exact, then we could all, of course, predict the stock market, and we'd all be rich and we wouldn't be in college, right? Well, maybe we would. I don't know. All right, so what's the company's revenue and what's its domain? Revenue, we just said, is X times P. Okay, with number of items sold, X times P, price per item, and we were just given this price function, so that would be my revenue. My domain, this 1 through 15, says that we know we can't make 1 million cameras, that we have a number here that maybe the number of employees we have, this is all they can make for the day. All right, let's complete the table calculating revenue. Revenue is X times the price function that we had. And so everywhere I see an X, I plug in a 1. So number of cameras 1, and this of course is in millions, then I would get my revenue. I can do the next by plugging in 3, and so on, to plug in all of these. Why would revenue start to drop? I mean, we don't know this company, right? But there could be reasons that once you start making to a point so many, it's costing you to reset up the machine, it's costing you to rehire more employees, and all that has to do with dealing with this price part right here that our analysts give us. Plot the revenue by the table values and then by our function. There's my table values. Notice this is an exact match. Why? Well, we got our function from our table values, so this would be exact. Nobody gave us any best fit line. We actually calculated these values based off of this equation, so it should match exactly. All right, the financial department produced the cost table below. So here is our cost function, and here is our data. We plot it, and of course, this is a best fit line, so it's not going to, again, be exact. Find the profit. How do you find profit? You remember, right? Revenue minus cost. The only thing to be careful of is notice these parentheses. You want to distribute that negative sign. So I can go through and plug in this equation. If the number of cameras is 1, I plug in X and I get my profit, which doesn't look too good, right? And so I can kind of see where things are looking a little better with my profit. What's happening with the profit? Of course, we kind of just said that it's going up and then it starts to come back down. Where is the company breaking even? In other words, where is revenue equal to cost? Meaning they're not making money, but they're not losing money. And a lot of times companies really want to know that. They want to find that break-even point so they know what to do to get above it and certainly not below it so they're not starting to lose money. The break-even point is where revenue equals cost. So if you graph it, it's these points right here. That would be your break-even points. How do you find these values? Do you remember that? Well, we just said where revenue equals cost, so we would set these two equations equal to each other, and coming up in the next lecture, we would see how would you actually solve that.